Morning everyone. Today we decided to sit in groups so that we can also do this as a group assignment. If you're not able to find seats, fine. Sit wherever you're getting a seat now. The idea is to collectively in a group try to work out some questions. Individually I think some of them can be a little hard. And then if time permits, we will also try and implement them. So if we go quickly, we should be able to also finish the assignment questions. Can you close the door? Okay, so we'll begin with a question where we're trying to find one nearest neighbor or just the nearest neighbor for a query point Q shown in the red color. And I've written Q belongs to a d-dimensional space. And our train set is also given to us, which is some endpoints which are also in some d-dimensional space. So as a first step for finding out the k nearest neighbors or the one nearest neighbor, we would try and create this vector which contains these distances between the query and each and every point in the training data set. So therefore this would be distance between QA, QB, QC, so on and so forth. And on the other side we'll just mention the distance. So if we were to find out this, if we have to write down the steps for finding the distance between a query point Q and any point A in the training set, what would these steps look like? I'm trying to find out the Euclidean distance between two vectors which are d-dimensional vectors. The reason I'm asking you all of these steps is so that we can come up with the time complexity analysis. So eventually I want you to be able to tell me what is the amount of time it requires for the training phase as well as the testing phase for k nearest neighbors. This is one very simple step in that entire procedure. Okay, what are the steps required for finding the distance between query Q and any vector A? This is simple, so we don't need a group discussion. Both of them are d-dimensional vectors and we're finding out the Euclidean distance. What do we need to do? So think of the naive approach first, not the programming approach. How do you mathematically define the Euclidean distance between two vectors, d-dimensional vectors? Square root of the sums of the squared distances. So it's Q1 minus A1 where the subscript is denoting the index for a d-dimensional vector. So we will do this. Now discuss in your groups and tell me that what is the time complexity of finding out the distance between one pair of points. In order to do this, you can decompose this operation, this mathematical expression, into all the underlying simpler operations. This is also one of the easier questions. So I'll give you 30 seconds for this. Discuss with the group, get me some answer. I want something like order of something into something or something plus something. Okay, what is the answer? What is the time complexity of this operation? Order D. So again, if we are trying to do this in a very simplified manner, we'll see that there are some subtractions happening, there are some multiplications happening, there are some additions, and then there is a square root operation. How many subtractions are we doing? D subtractions or order D subtractions. Multiplication, squaring, I'm just writing as a multiplication. Additions is also D, square root is 1. Assuming all of them take constant time, the total time for one such pairwise distance computation is order D. Okay, what is the time required for creating a table like the following? We have n points in the training data set. Order of n times D. where D is the dimensionality, N is the number of samples in the training data set. Is this a problem? Why or why not? So now you have to think of where might you be using k nearest neighbors like algorithms. And from that angle, you should think of whether this is a problem or not. So would you say that this time complexity, is it linear in n? Is it sublinear in n? Is it polynomial in n? Is it exponential in n? What would you say? The time complexity is linear in n. Therefore, as n increases, you'll require much more time for this distance computation. Now, some of the applications might be that, let's say Amazon wants to recommend you some product. How many products do you think Amazon might have? Millions, billions on their website. Each product, let's say that they are encoding as a vector, as some d-dimensional vector. And each person on their website is also represented as a some different dimensional vector. So if I want to figure out what products are similar to one product that I'm searching, I need to search for millions of products in some higher order space, vector space. Right? As an example, if I have a shoe may be described by some various attributes, some d-dimensional vector, and some other categories would also be represented by the same vector space. Now, given a shoe, I want to figure out, are there any other similar products or not? Or if the Amazon team wants to figure out that who is similar to me, and let's say that Ayush has similar interests as me. So we need to do a lookup in this higher order, in this high dimensional space of millions of users and find out who are the closer ones to me. Once we find out that, we can then say that perhaps whatever Ayush likes, I will also like. Right? So this is where the problem is occurring. We typically have millions, billions, trillions of such records. So even a linear algorithm is very slow. Okay, so that was the complexity of creating this table. But that does not end the problem. As I mentioned, our goal was to find one nearest neighbor. So imagine if we have created this distance vector, how much time would it now require us to find out the one nearest neighbor? So we have to do a linear search amongst all the n examples. We can't do anything better than that because we're not given anything sorted, etc. So therefore, the overall time complexity of finding one nearest neighbor is order nd. Right? Now, I purposefully went very slow in this, and you might have been bored to death. But I just want you to think of these steps when you sit for interviews or when you write your answers in some quiz or you're trying to solve a problem, so that at least you can partly show that you know the basics, you know the different steps involved. And even if you're wrong somewhere, you don't give the overall wrong answer. You get at least some part marks. You show the approach that you're taking. And you also understand that where the main problem is occurring. Here, the main problem is occurring when you're trying to compute this distance vector. The distance vector showing the distances between the query points and all the points in the training data set. Okay, so then our goal is to reduce this time complexity. There are two things you can reduce. One is reduce D, the other is to reduce N. We will be targeting the reduction of N, and you have to tell me how we can do that. The topic of the lecture I sent already on Slack, it's approximate algorithm. So whenever you're doing some approximations, you will lose out on something and you'll gain in something. What we want to gain is reduce this ND into something better. So for folks who have taken the data structures algorithms courses, typically when we say that if a linear algorithm is slow, what kind of an algorithm do we try and search for? Where the complexity is logarithmic in N. So now I want to ask from you the intuition as to how you might go about reducing this time complexity. Think about the various steps you can do. So discuss for a minute with your group, and then I'll ask some groups to give me answers. One hint is to think about the algorithm which we first studied in this course. The first algorithm that we studied in this course. What was that? Decision trees. Can you think of something which decision trees do, which will make this problem easier. Okay, let's hear some answers now. Does anyone want to volunteer? Okay, middle column, fourth row. Yes, you people. Majority blue and black. Yes. Any answer is good. Okay, the row behind them. Go ahead. So think of this as a quiz. You have to write something. You have 20 minutes left in the quiz. You have to write some longish answer. You won't leave it up. Okay. Okay, good. So the main problem is coming because we have to find out the distance between the query points and all the training samples, all the samples in the training data set. What if we took a subset of those? Now, how do you take a subset? Perhaps you take a random subset, that is one approach, or you take a more structured subset. There could be various approaches. The hints which I want you to consider is, think what decision trees do. What do decision trees do when they try to classify or regress? They recursively split the input space into smaller subspaces. Now, using that, can you tell me how you can reduce the time complexity? So the idea is that we want to find out the distance between query point and a smaller number of points from the training data set. How might recursively splitting or how might splitting the input space help you? What do you think? Okay, the first row side. How might recursively splitting the input space help you to reduce the time complexity?
We can do something like decision tree. So over there, then decision tree will help us to read some particular subset of the data.
Okay, that's it. I mean, that was the answer I was looking for. Instead of looking at n examples, look at what decision trees do. They divide your samples into smaller subsets, into smaller regions. Now, if you can take some branch, some path from the root to the leaf, you would be now considering a smaller set of examples. So that's the key idea. We want to be reducing the number of examples which we want to compute the distances against. The other hint is that the current algorithm, which we looked at, the naive or the exact variation or the brute force variation of k nearest neighbors, we said it is a lazy algorithm because it does nothing at the training time. So that's another hint. Can we do something at training time which would reduce our testing time? So thus far the problem that we've been talking about is somehow reducing the time it takes to query, not the time it takes to train. Because in the exact algorithm there is no training time also. So think again of a production setup like Amazon or Facebook or Microsoft or anything. They want the responses to be very quick, but the training can happen can happen at some other place, and it might take, let's say, 1 day, 2 days, but that is not shown to the user. The user quickly wants to get the response in milliseconds. The latency at that end needs to be reduced. So therefore, it is okay to take some time at the training phase if that can somehow reduce the time it takes at the testing phase. So these are a few hints. We will be looking at the first such algorithm, KD trees. I have borrowed this set of slides implementation from a very nice lecture by Victor Lavarenko. We are given these, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points in this 2D space. I'll directly walk over the algorithm. So it's a two-dimensional data. I pick up my first dimension. Let's say I pick up x1. I could have done them randomly or I could do them in round-robin fashion. Let's assume I pick up in round-robin fashion. I pick up my dimension x1. I find the median of all the points along the x1 dimension. So I am looking at the first coordinate only, 1, 2, 4, 3, 5, 6, 7, 8, 7 and 9. I find out the median across these and I get the number 6. Once I get the number 6, I draw this tree-like structure where x1 is less than 6, true and false. Because I've chosen the median, I get half, roughly half. The elements in this part of the tree and 5 elements in the right part of the tree. Now I repeat this procedure where I now pick up dimension x2 and let's pick up this part of the tree where x1 is less than 6. So this subspace we're looking at. Now we still do the same thing. Can you tell me where the next partition will occur? At x1 equal to something or x2 equal to something? Can you tell me the partition which occurs in this space? Firstly, you'll have to be looking at the second dimension. So you want to find out the median along x2 of these 5 points, which will be the median of 1, 3, 4, 7, 9, which will be 4. And then I again split this tree as x1 less than 6, x2 less than 4. Now this gives me 2 points here, 3 points here. Similarly, on the right part of the tree, I do the same procedure. And I'll get a partitioning like this. So therefore, now I have 2 levels. And I have now two elements, 3 elements, 2 elements, and 3 elements as the leaf. Now, if I have to, given a query point 7, 4, this point, I want to find out its prediction, find out the nearest neighbor for this. Now, for that, I walk down the tree. I first see that the first dimension 7 is 7 less than 6, false. So I go into the right part of the tree and then I look at the second dimension 4. Is it less than 8? Yes. So it will look at these 2 points, 7, 2 and 9, 6 as the potential set of points over which I want to find out the nearest neighbors. So I will look at these 2. In fact, I'm not looking at this third one because that's gotten the other part of the tree, which is x2 equal to 8. So therefore, it's in the other part. Now, given these 2 points, I'm trying to find out amongst these the closest neighbor. So therefore, can you see that now I'm searching only over 2 examples. Previously, I had to search over 10 examples. And this is a very contrived, very simple example to just illustrate by how recursively partitioning the input space, you are reducing the number of computations or the query distance computation you want to take. Now, if you're following along nicely and I see 2, 3 people getting very offended at this slide, you should be getting offended at this slide. Why? Because this black point seems to be closer than the others, right? So as a consequence of the positive benefit that you're getting is that the way less number of comparisons are needed. The negative is that you might actually miss out the closest neighbor. Now, I'll leave this as a homework exercise, which you always know that if such questions are left as homework exercise, they are good questions for follow-up quizzes. That what should you do in order to mitigate such issues? Where there are points lying in some other subspace which are closer to the query point compared to all the other points which are there in the current subspace. Okay, now this is where it gets fun. I want now you all to think about in groups, find out the time complexity for training as well as for testing. First, we'll start with training. You have to remember the procedure. We figure out the median along one dimension and then we split. Then we find out the median along the other dimension. Let's assume we're doing in round robin fashion. And we do that till certain extent. How much time would it take to create this tree structure? At this point, it's no longer a machine learning question. It's more like a data structure algorithm question. The first hint which I want to give you is that if there is a depth 1 tree, the number of samples which are at the root, at the leaf, are n by 2 and n by 2. If we have a depth 2 tree, we have n by 4, n by 4, n by 4, n by 4. So you have to figure out that when we eventually walk down some path, what is the number of samples that you will be effectively comparing against. That is one thing you need to do, and other things are similar. The other timing consideration you'll have to take is that what is the time required to find out the median, to create this data structure. Let's try for the next 2 minutes. The best approach would be to boil it down to the number of additions, subtractions, multiplications, or just reuse some of the previous results. So we keep going down this path. Can you see that the depth of the tree would be log n base 2? Because at each stage we are dividing it into 2 partitions. So we have log n base 2 levels in the tree, and for each level, what are we doing? So for each level of the tree, so this is the first level. We pick a dimension, which we assume is free. We find out the median. How much time does it take to find out a median of some numbers? So there are various algorithms you can do for finding out the median. How many have heard of the median of median algorithm? There's a median of median algorithm. You could simply find out the median by sorting a set of numbers. That's a trivial algorithm. So that is one thing you have to do. But in what dimensional space are you finding out the median? Is it one dimensional or is it a d-dimensional? In one dimensional space, you're trying to find out the median, which is a huge benefit that you get. You find out the median in one dimension. So if you have n examples, you want to find out the median, you can do that in n log n time, because by sorting and then just finding out the median. The number of levels is log n base 2. For each level, you have to do this sorting. Right? So the total time to build the data structure would be n log n into log n, or log square n. Right? So that's the first time that you need to consider in building up this data structure. Typically, when we execute this, we don't go to log n base 2. If we go to log n base 2, what is the number of samples in the different leaf nodes? Each of them will have 1. And if you have 1 sample, there is no point in doing k nearest neighbors. So typically, these stop at some s samples, which is, let's say in this case, it's 40 sample leaf size, at which we stop partitioning. So there are two benefits to it. One, which I just told, that you don't really need, like if you have to figure out 5 nearest neighbors and you have just 1 point in that leaf node, you can't find out that. So you typically want some number of samples to at least find those number of neighbors. What could be the other reason to stop early? Why might it be useful to stop partitioning after a certain point? Okay, one, partitioning always introduces some notion of approximation, which means that you could miss out on points. That's another very good point. Okay, what could be some other? Even from time perspective, is it beneficial to stop at a certain point? Why? The overhead of partitioning is going to be more than just doing a brute force search if the number of points is very small. Okay. So if you're only trying to search over 40 examples, it's perhaps quicker to just do a brute force search as opposed to doing recursive partitioning. So you have to consider both of these trade-offs. Where do you think I got this number s equal to 40 from? So I got this from the sklearn documentation. If you look at sklearn neighbors KD tree, leaf size positive, integer default to 40. Number of points at which to switch to brute force. So brute force means the exact algorithm. They have figured out, they've done some benchmarking and they have found out these things. So for now, let's assume that the leaf size is 40 and not 1, and we don't go down log n base 2 levels, but we have some reduced number of levels. So given s points in my leaf node, what is the time complexity of querying? How many think it is S into D? The time complexity of querying is S into D? No one? How many think it's S into D plus something else? Okay, what is that plus something else? That plus something else is the number of levels it takes to reach the leaf node. Right? Not the number of levels, the number of computations it takes to reach the leaf node. But first, let's figure out how many levels it takes to reach the leaf node. Let's approximate it to be log n base 2. How many computations do you require per level? So there are n levels. At query time, what happens? Let's go back. If I get a query point 7, 4, I first look at the tree and the first index I'm looking at is x1. I compare 7 with 6. How many computations did I require? 1. At the next level of the tree, I do this comparison of 4 with 8. How many computations did I require? 1. For each level, I require a single computation in one-dimensional space. So therefore, when we traverse down the tree in some log n levels, and at each level we need a single computation. So therefore, the total number of computations required to reach the leaf node is log n. And then once you reach the leaf node, you have S examples. To figure out the distance between a query point Q and S examples, which are all d-dimensional, you require d into S time. So therefore, the overall time which is required is log n plus d into S. Typically, d would be much smaller than n. And if S is also small, then the time required is logarithmic in n. Right? We made some very simplifying assumptions. If S is small, like 40 is a small number, and if d is much smaller than n, it turns out to be logarithmic n. Otherwise, you can have the full expression, logarithmic n plus d into S. The important thing here is that the query time is now not linear in n, but it is logarithmic in n. Now, what does it come at what cost does this come at? What are I'm just showing you the positive sides of this algorithm. What is the other trade-off which you get? You can miss a few points, that's one. Second, the training time is not 0. Previously it was 0. Right? So therefore, whenever you're considering such questions, you should always think of the various kinds of trade-offs and then engineer it to your companies or to your problem statement. Are you okay with missing out on a few samples? Are you okay with neighbors? Are you okay with increasing the time it takes to train? So all these are the kinds of questions you want to consider. What does it take if I now put some 10 new samples in the training set? What will I need to do? Do I have to train from scratch? Can I reuse the existing implementation, existing tree? What would it need to do at the test time? So all of these questions you should be thinking. The next approximation algorithm is known as locality sensitive hashing. I'm picking up a very specific implementation which is called random projection. I'm again borrowing the slides, the algorithmic details from machinelearninginterview.com. What if your k is greater than s? So he's asking the question, what if his k is greater than s? Then you'll have to see, perhaps you'll have to walk upper in the tree. Or don't have such conditions where k is greater than s, right? Or have s big enough. I mean, there are various kinds of solutions. I don't know a single best answer. But if s is very small, you would have to perhaps go up the tree, backtrack, and consider a larger number of samples. How many of us have studied hashing? Where do we use hashing? When we are trying to do what? Sorry? When we're trying to search some content, when we are trying to use, like Python, the dictionary data structure would also use hashing, hash maps in Java. So all of these are various data structures which we use. We'll be using similar techniques, but in a different connotation. So there, in regular hashing, our goal often is to reduce the number of collisions. Right? Here we will want to ensure that all the similar examples are put in a similar bucket. So I'll directly go on to the implementation. The goal previously which we saw in KD trees was we are doing some random partitioning, not random partitioning, we're doing some axis aligned partitioning of the space. Right? KD trees would do axis aligned partitioning of the space. Now let's see if we can do some non-axis aligned partitioning of the space. So let me pick up any hyperplane in this dimensional space. The equation of hyperplane would be summation wi xi plus b equal to 0. Right? So I pick up one such plane, and can you see that this plane is dividing the data set, the data points into two subgroups, one which are above this and one which are below this. Now, how would I mathematically figure out or in code figure out that f is above this hyperplane and c is below this hyperplane? What do you think I need to do? Put the value and then check the sign, right? So for f, g, h and I, summation wi xi plus b would be positive, and for a, c, b, e, d, j, summation wi xi plus b would be negative. So wherever the sign is positive, I will encode that with a bit 1, and wherever the sign is negative, I will encode that with a 0 bit. So therefore the point A gets assigned a 0 bit, and so on and so forth. So I've done this random partitioning of space, random because I had randomly chosen these W's and B's. There was no as such specific structure like KD trees. KD trees had a very specific structure. You look at the median of the data. Here you didn't need anything like that, randomly projecting the data into some different space. I can similarly pick up another hyperplane, H superscript 2, and I look at the points which are above this and points which are below this, which decide my next bit in this table. So therefore I get A is above this hyperplane, so therefore it gets assigned the bit 1. So therefore now you can see in this space, I've used two hyperplanes. How many subregions have I got? 1, 2, 3 or 4? 4 subregions. In how many subregions do I have points? 3. Right? If it were done perfectly, or if it were done with a larger number of such hyperplanes, we would expect to have roughly equal number of points in each subregion. But that doesn't occur here. So we look at the different subregions. We look at this subregion where the bit sequence is 0, 0. So it's these points which are below the first hyperplane and below the second hyperplane, the intersection of these. This gives us 1, 2, 3, 4 points. Similarly, I can look at this region where where the points are above one hyperplane and below the other hyperplane, and the third one where the points are above both the hyperplanes, and there is no set of points in the fourth subregion. So we'll just leave it for now. Now, what do you think we will need to do? Okay, before I go on to that, the querying and the time complexity, let me discuss how you might go about doing this random projection. To sample a hyperplane for a d-dimensional, so hyperplane will be defined by a d-dimensional w vector and a bias vector, bias value b. It's similar to how we were doing in neural networks. Summation wi xi plus b. So I sample these wi's and my bias from some normal distribution. Right? The details are not relevant at this point. They'll become very relevant when you try and implement them, and I'll show you why you have to be a little careful with the initializations also. So you randomly get these values, w's and b's, and then you get an equation of a hyperplane. And then when we want to get the hash code or the bit for corresponding to a particular hyperplane, all I need to do is to calculate summation wi xi plus b for a particular x vector and find out the sign for it. Right? So if the sign is, if it is a positive number, I assign a 1. If it is a negative number, my output is a 0. Okay, question to all of you. I want to vectorize all of the things, all of the procedures which I am following for locality sensitive hashing with random projection. And there is also projection element to this entire thing, which I have not yet explained. So discuss with your groups, with your group members, and tell me a way in which you can vectorize these computations. I don't want to be going over an individual sample, computing summation wi xi plus b and doing a sign, etc. I want to do something much more quicker. And I want to do this over multiple hyperplanes. I don't want to be writing a loop over the hyperplanes also. So therefore think of what vectorization, what matrices you might do. And let's assume that we have p different hyperplanes. We have p different hyperplanes. The first question, if you have a single hyperplane, how would you vectorize summation I wi xi plus b component? How did we do this same procedure in linear regression when we were given a matrix X? We added a column of ones. So I'll create x dash as a column of ones, and this is where the main trick comes in. Let the number of hyperplanes be p. So I create this W or this R matrix as this D cross P dimensional matrix, right? Where each of the entry is coming from a normal distribution with some mean and some variance. So each we have D rows and P columns. The reason I've done this is to ensure that I don't have to do for individual hyperplanes all of the calculations. So then if I do X prime into W, that gives me n cross P dimensional matrix. If I take the sign of that, I will, for the n points and the P hyperplanes, I will get whether each point is above or below that hyperplane, right? So if we come back to the question, our objective was to see for each of the P hyperplanes, each of my n points in my X dash, are they above the hyperplane or are they below the hyperplane? So therefore I needed an n cross P dimensional matrix. Even from a shape analysis you can figure this out. And I have generated this W matrix using this normal distribution. So I get a n cross D dimensional input matrix augmented and a W cross P dimensional projection matrix. And then when I multiply these, I get n cross P projected matrix, and correspondingly I can get the sign from it and I get my hash code. Okay, now question for all of you. Can you figure out the time it takes to create at the training time? What is the time required? at the training time, what is the time required, and what is the time required at testing. Again, you have to think of the operations required. You are generating this matrix that would require time. You're doing some multiplications, matrix multiplication that would require some time, and so on. So if you notice, at this stage, we have not even talked about the testing phase. We are just talking about the time required for the training phase, which is given some n data points. You want to figure out whether they are above or below some p hyperplanes, which is you want to create this n cross p dimensional binary matrix. So I want you to find out the time required for that, for creating this n cross p dimensional binary matrix. Okay, what is the time required for creating this H matrix? For now, just assume that there is one set of hash functions. We'll come on to why we might need more set of hash functions. We require p hyperplanes. So if we have to find out the sign of x into R, which is n cross d into d cross p matrix, that would require n dp time. And if you were to generate the R matrix, that would require dp time. Let's assume that each individual element, when sampled from the normal distribution, takes some unit time. So therefore, at training time, the time which you require is order n dp. Is everyone on the same page? Okay. Now the time required at the testing phase. Can you tell me that? What? Sorry? The sign would also require the same time. So NDP plus NDP. Okay, what do you need to do at the testing phase? Do you need to do something similar to KD trees? In KD trees, you had to walk the path from the root to the leaf, and then over the leaf node set of samples, you did a exact search or a brute force neighbor search. What is the difference here? When you get a new query point, what do you need to do? For a new query point, you would have to you have to compute its hash, or you have to see whether it's above or below certain hyperplanes. Right? So you basically first need to localize the hyperplane. Right? If my test point is here, I need to first localize my hyperplane, which means that for a query point, I need to compute this hash vector. Right? Is it above a certain hyperplane? Is it below a certain hyperplane? So that would require dp time. right? Because it's a d-dimensional multiplication that requires summation wi xi plus b is is order d, and that you have to do for p such hyperplanes. So therefore, order dp time is the time for computing hash for a 1 cross d or a d-dimensional query vector. And then let's assume that if we have t points in the bucket or in that sub-region, then the time required would be t into d, right, to find the closest neighbor. So on average, what would you expect t to be? Or in a very good, well-balanced split, what would you expect t to be in terms of n and p? N into something, n divided by something, 2 to the power n, something like that. Can you think? N divided by? So can you see the t if in a very well-balanced hyperplanes, datasets, etc., would be approximately n over 2 to the power p. As each time you add a hyperplane, you are dividing the dataset into 2 partitions. So therefore, the test time might be order of d into p plus dn over 2 to the power p, right? So dp time for computing the hash and dn over 2 to the power p, which is t into d. If I just substitute the value of t equal to n over 2 to the power p, I get this expression dp plus dn over 2 to the power p. Now, if we further simplify this, okay, I'm not further simplifying this, but you could also think in terms of if p is some number of specific number of levels, let's say logarithmic in n, something like that, you can then get something even more simpler, right? You'd again get something like d into logarithmic of n. If p is, let's say, on the order of logarithmic of n, you'd get something like d into logarithmic of n, and then dn over 2 to the power logarithmic of n. You can compute those things. So any questions in these implementations, in these different implementations? So so the question is, once you find out the hash, how do you know the other points in the bucket? I have left this specific implementation detail aside, but I would say that let's assume that you get an order 1. So I'm saying let's assume that that's constant time. So let's assume it for now, that that the lookup time is constant, or you have stored for each. So think of it as you've stored corresponding to 0, 0 wattle points are there. So in the training phase, you can accommodate and have more complexity there. Other questions on these implementations? So if we have to summarize these implementations, we said that the main problem in the exact or the brute force algorithm is that the querying time is linear in n. We somehow want to reduce that. Our approach is that we somehow reduce the number of comparisons which we need to do. We have taken 2 such approaches. The first one being we recursively partition the input space into smaller subspaces when in an axis aligned fashion, and then we just look at the subset of the tree, subset of the samples. Of course, because it's approximate algorithms, it can lead to situations where the actual neighbor is not being found. And this is also the last part of your question 2 in the assignment. Can you find out that how many of the closest 100 neighbors or n neighbors are you missing out because of the approximation that you're doing? Like in this case, it's missing out it's missing out the closest neighbor. We then looked at the second variant, where instead we looked at splitting across non-axis aligned fashion by using some random projection or using some different hyperplanes. And if you want to read more about the specifics and which gets used when, we can just look at this very good guide from K-nearest neighbors. Right, so to talk about the brute force algorithm, Here they've written dn square because they're looking at all pairs of examples. So therefore, just multiply that dn with n. And then they mention these algorithms, KD tree, and then why ball tree is a better algorithm. And this is very interesting, where they mention that how they figure out the optimal algorithm given some n samples and some dimensionality d. They mention that for low dimensional data, KD tree is a good algorithm. For high dimensional data, you should prefer random projection, etc. It's a good, interesting read. And then the effect of the leaf size, which we said that let S equal to 40. How did they come up with those? So they have given up some such justifications. Okay, so we still have 25 minutes. We will now do some implementation. I will share, let me share the link to the notebook which I want you to download and work in groups. You can either do that over Collab or you can do that over your local editor. If you already have the ML teaching repo, you could just pull the changes. Otherwise, I'll give the exact link. And then I don't know if you know this or not, but Collab also you can open any GitHub, any notebook hosted on GitHub. So you could go to GitHub and then, I don't know whether the full path will work or not. Yeah, you could go to GitHub and give the full path and that, Collab, and that should also work. How do folks typically download notebooks? If someone gives you a notebook link, what do you do? Like in this case, one, you could clone the entire repo, but that might be slow. What would you do? Sorry? This is not a difficult question. How do you download a notebook? I'm just wondering if there are better methods than what I do. No one's interested. Okay, I'll let you download it, whatever. So I'm assuming you'll keep downloading in the background and you'll set it up in the editor. In the meantime, let me just show you the way I wanted, one specific way in which I wanted to think about solving such assignments. I have first created this dummy dataset, which is the same dataset I'm using in the class. So I always recommend doing such things where you can work out an example perfectly on pen and paper, and then the same you're trying to get it working with code. I've created this 1923 dataset. And just to help me, I have done a bunch of things. Like one, I've added the grid lines. I've also added the grid lines at step of 1. If I didn't use the default grid lines, I have colored the train points and the test points differently. Right? So these small changes will make it slightly easier for you. Now, looking at this, you can immediately see that the closest neighbor to this is 2 points. One is 5,4, the other is 7,2. So you'd expect any library to give you these two as the closest neighbors where the distance is 2. So the first thing I'll do is, instead of one nearest neighbor, I'll just show 2 nearest neighbor to pick up both of them. I always recommend first using very nicely implemented or existing implementation from sklearn. So in this case, I'm using sklearn.neighbors import nearest neighbors. I get nearest neighbors equal to k, algorithm equal to brute force, exact, and then fit x. And then I get the distances and the indices for the query point. My query point is 7,4. if I run this, I get the closest 2 points to be 54,72, which is expected, and the distances to these points being 2, 2, which is again expected. When you have to implement the KNN algorithm from scratch, and if you go back to the discussion, the first thing which we said was, let's try and find the pairwise distances between two vectors. So therefore, I would also recommend you implement that first, which is what I'm showing here. I discussed about the naive implementation, where you, and I've also done some bit of annotation here to help you to understand that my x and y have to be d-dimensional vectors. My output is a float. I check the length of x, find out d. I assert that length of y is also the same. I initialize square distance to 0.0. I iterate over each of the d dimensions, and I find out the squared distance and find out the square root of that distance. I can also simply use NumPy and broadcasting techniques. I can just do x minus y squared and find out the square root, or I could do the L2 norm between the x on the x minus y vector. All of them should give me equivalent answers. So I would always suggest we do these kinds of sanity checks. Given some simple data, we ensure that the different algorithms give you the same answers. Now, if I am to do some timing analysis of these three versions, which one do you expect to be the slowest? The first, second, or the third one? Which one do you expect to be the slowest? First one. Okay. Let's do the timing analysis. .78 microsecond. What happened? The NumPy version seems to be slower. Is the laptop giving you wrong numbers? Is the code wrong, or are we doing the testing wrong? Any thoughts? Why is the naive version using the for loops which are written in Python slower than what we are getting using the NumPy version, which is using much better compiled C code? Or what do I need to do in order to do a better fair comparison? So typically when I give you questions in the assignment, do I tell you to do the timing comparison just on one single example? No. Okay. First, you're doing this over a single example. Second, so the n aspect comes in, just one example. Second, the dimensionality of the data is very small. It's just two-dimensional data. Okay. In order to get the benefits which NumPy and broadcasting and compiled code and all of that will give, you'll have to typically have a larger number of examples and higher dimensional data. So do that as an exercise to figure out. There will be a point after which the NumPy implementation will start getting significantly better. Now, if I go back to the slide, and again I'm showing this purposefully because this way we can look at the slides and look at what function I need to implement. And then you can very nicely compare both these. The next thing which we discussed was to create this table or this vector having the distance between the query point and all the samples in the training data set. So this is where I will want you to write some code. I have given you some starter code. N comma d is my x dot shape. So I get my n samples d-dimensional vector. My query point is a d-dimensional vector. And my output should be a NumPy array of how many points? What should be the size of my output? N or D? N, because we are trying to find out the distance between query point and n training points. So distances I have initialized to zeros of n. Can you now write some code here? In a notebook? Is everyone able to set up the notebook, get it to work? Has anyone written the answers? The simplest is to, can you just write it with a for loop first? It's okay to write with a for loop. And then if you want, you can make it more sophisticated with broadcasting, etc. But for loop is okay for now. Okay, so I'll assume you'll be able to write a for loop here or do some trick. But after that, you want to check whether the function that you've written is correct or not. Again, can you use a reference implementation to compare this against? Turns out we can. If we run the nearest neighbors algorithm with from scikit-learn, giving x neighbors, length of x neighbors, and the brute force algorithm, and if we run this algorithm over the query point, we will get them in a sorted distance fashion. We'll get 2, 2, 2.8, so on and so forth. But we don't really need it in a sorted fashion. We need it in the fashion A, B, C, D. I can then just index the distances with the correct indices in order to get them in A, B, C, D fashion. So I get now the distance between query point and A point, query point and B point, so on and so forth. I can also just simply create a pandas data frame, which gives me if x1, x2 is something, then what is my query distance. So I'm doing all of these things so that you can go back to this plot and verify if the numbers are making sense or not. Secondly, you should then benchmark your implementation of finding out the distance vector from the query point to all the points in the training data set via this logic. Right? So this is the function which will get repeatedly called whether you're using KD trees or whether you're using LSH with random projection or exact KNN. This is where when you finally decide what number of points, what points you want to compare against, which will then you'll be using this function. Right? So you want this function to be very quick. So therefore, it might make sense to spend some time and ensure that you have well implemented this with broadcasting, etc. Once you have done that, and let's say we want to now come on to the second algorithm, which is locality sensitive hashing with random projections. I will first define my number of hyperplanes p equal to 3. I've specifically set a seed so as to get somewhat reasonable results here. I do my R matrix, my random projection matrix, to be a random matrix of size x dot shape of 1 plus 1 comma p. Why am I doing this plus 1? To add the bias component or to have the b component. So if I do this, my R matrix looks like this. Why is it 3 cross 3? Because it's a d plus 1 cross p dimensional vector. D was 2, so d plus 1 is 3 and p hyperplanes. For some reason, for just to make things slightly better, easier, I'm just making these last columns as just ones. We don't need to do this. This was just giving me somewhat reasonably looking results. So if I draw these different hyperplanes, I get this hyperplane 1, 2 and 3. This is not a very good split, not a very good set of hyperplanes, because for the green hyperplane you can see all the points are above this. You typically never want such situations. You want it to partition into some way. The orange and the blue are okay, but they are fairly similar. So it's not a very good partitioning. This is what I meant, that you'll have to be a little careful with the way you initialize these different weights, and you can read some rules of thumbs on the internet. Once we get the x augmented, this is when we finally want to do the calculation. I get the x augmented by stacking ones. So I'll get ones, column of ones, and the first point 1, 9 and the last point 9, 6. I can do x augmented matrix multiply R, and I get another matrix of size n cross p. Right? So I have projected my points from a d-dimensional space to a p-dimensional space. And then I look at the sign of this matrix, H matrix. It will be ones and minus ones or ones and zeros depending on the specific way you implement. And then you can use this R to compute the hash for the query points. Look at the specific subset of points which have the same hash, which, as Kishan was also mentioning, might be free, might not be free, depending on how you implement it. You could also store for different hash indices or different hash buckets, you could store the set of points there. Or you could do this at the test time, which might require some more time at test time. So I wanted to show these specific implementations going from the very naive implementation, exact implementation, comparing to the scikit-learn implementation. The figuring out the most important function, which can be bottleneck, which is the pairwise distance computation, and then doing a okayish example for locality sensitive hashing with random projection. You will have to improve this. For the KD trees, you could use some of the code which you had written for decision trees. Any questions? Okay. If not, thank you. We will meet on Monday.